Okay, good morning, everyone. So I hope you are keeping safe and dry this very rainy day, especially to those in the Calabarzon or North Luzon areas. But yeah, how are you guys? Oh, first, can you hear me?
Sir.
Ulan din po.
Hold on, may problema yata sa audio ko. Wait lang, guys. Okay, so for today, we'll continue Module 4 and try to finish it. And if we finish early, we can start with the first few parts of Module 5. Just a heads up, Module 5, I'm still finishing it, though most part of it is just reintroducing some things that you might have known from your study of matrices back in your undergraduate or graduate linear algebra courses. So medyo maraming definitions yung Module 5. And I'm thinking whether to complete homework 5 in that module by giving actually by giving 3 problems, or wait for another module to give you to um, to just have say 1 problem from module 5 and 2 problems from module 6 to complete homework 5. So I'll keep on thinking about that, but hopefully by tomorrow I can upload module 5 so that you will have probably 2 or 3 days to work on the homework there. Because I think you're already doing 2 of the problems in the homework, and then I think we only have 2 full weeks before the semester ends. So, which I think is still a good timeline for us because we can talk more about the algebra of matrices or different applications of matrices that you might not have encountered in your lower linear algebra classes. So kaya medyo i-skip ko yung halimbawa um, Gauss-Jordan elimination, techniques in solving linear systems, because I think these are things that you are well versed with. So probably let's try to introduce something new, something that probably most of you have not seen before, para may madagdag, may mapulot kayong bago from this linear algebra class. All right. Last time, I think we have established the equivalence between the set of all homomorphisms or linear transformations between two vector spaces of the appropriate dimensions and the set of all m by n matrices, right? So we have developed sort of an algorithm on how to translate a linear transformation and find its matrix representation, right? So, and that representation will be unique because the equivalence is an isomorphism. It's an isomorphism, so that means it is monic. So if we have two linear transformations that have the same matrix representation, then we have proven that those two linear transformations must exactly be the same, right? So kaya kung meron kang linear transformation and the ordered basis for both the domain and the codomain, then you're guaranteed to find one and only one matrix representation for that linear transformation, right? And that is due to the fact that uh, the mapping that we have established between hom of VW and m sub m by n of f is monic and epic, right? But we haven't seen yet what is the implication of that mapping being a linear transformation itself, because we said it's an isomorphism. So it's monic, it's epic, and it is a linear transformation. But one of the results towards the end of the of this module will tell us what's the implication of it being an isomorphism. All right. And then we look at several examples and play with different linear transformations and ordered basis for the domain and the codomain, and try to find the matrix representation for a given linear map. One thing that I want to emphasize there is that the matrices that you get from that algorithm will act on vector of coordinates. All right. So if you have a matrix M, you have a matrix, sorry, not curly M, but if you have a matrix M, right, that say is a representation for the linear transformation, it will act on a set of coordinates. It doesn't act on a vector on your domain, because number one, your vector space might be abstract. It doesn't necessarily need to be comprised of numbers, right? So what the matrix does, or the matrix representation does, is that it acts on a set of coordinates, right? And the set of coordinates is actually another vector, but not from the vector space V, but from the vector space F to the N, right? So pag mag-evaluate kayo ng image ng isang vector under a linear map using the matrix representation, kukunin niyo muna yung coordinates ng vector na yon. So when we say coordinates, they are the scalars in the basis expansion of that vector. Tapos saka nyo siya i-multiply dun sa matrix. And then what you get as a product of the matrix and the vector would be another vector. But that vector, so the product of your M alpha is another vector, but it belongs to F to the upper M. It doesn't belong to the codomain W or to the range of L, but it belongs to F to the upper M, which is the vector consisting of M tuples of field elements, right? And what does F of M mean with respect to the vector space? F to the upper M is the set of all coordinates for the images, for the elements of the codomain with respect to the ordered basis. So ang nakukuha natin sa matrix multiplication ay hindi kagad yung image vector. Pero nakukuha natin sa kanya ay yung vector of coordinates. Kaya kung makikita nyo in previous examples, when we illustrated how to use matrix vector multiplication to find the image of a vector in V as a vector in W, nagko-convert pa tayo between coordinates. And since this involves using coordinates, which would be the scalar coefficients in the basis expansion, the choice of ordered basis is very important, both for the domain and the codomain. So we have seen that if you simply rearrange the elements of your ordered basis for either the domain or the codomain, the matrix will be completely different. Not completely, but a rearrangement of the matrix representation that you originally found. But if you completely change the ordered basis, then you will get a completely different matrix. But in the end, as we expected, we will get the same images under the same linear transformation, whatever matrix representation we chose. All right. Now we'll start the meeting with illustrating how the reverse process works, because we said that HOM and the set of all homomorphisms is isomorphic to the set of all M by N matrices over the field F, right? So that means we have shown last time that any linear map has a matrix representation. But let's see now how a matrix gives rise to a linear transformation. Now let's consider example example 53, where we consider the matrix A, this 2x3 matrix over the set of complex numbers. So 3, 5, 7, 4, 8, 2, okay? And remember that a matrix can only be prem-multiplied to an n by 1 vector, right? For your matrix multiplication to work, if we're multiplying A and B, A should be m by n, B should be n by m, right? And what we want to get as a result is a one vector, right, of certain length. So we want to prem-multiply matrix A into an n by 1 vector. Okay. Um, okay. There we go. So in doing the matrix representation, we would like to choose the proper dimension for our domain and codomain. So when we translate a matrix into a linear map. So since we have a 2 by 3 matrix, which can only be multiplied to an n by 1 vector, actually in general, but to any n by p vector, right? But since we are expecting a one vector back, so that means we only multiply it by n by 1. So that means the elements of the domain should be of length n by 1. But what are these vector representations are? So they are really the scalars in the basis expansion. So if you want an n by 1 vector to be your set of scalars, then your vector space V, the domain, should be of dimension the number of columns, right? So it should have dimension n. So here, this is our m, this is our n. We said that the domain should comprise of n by 1 vectors, or the domain of A should be an n by 1 vector. So we choose the dimension of the domain vector space to be equal to 3. So the number of columns always represent the dimension of the domain. So you can pick any vector space V as long as it has dimension 3. You could choose any abstract vector space that we have seen last time, any crazy vector spaces that we have dealt with in the past. But just for simplicity's sake, and I think I promised that we will sort of transition to the more tangible vector spaces. So okay, let's consider V to be R3. Okay. So also, if you multiply a 2 by 3 matrix or pre-multiply a 2 by 3 matrix to a 3 by 1 vector, we get back a 2 by 1 vector. So that means if you get the product A times an n vector, so this should be an m by 1 vector, right? So that means pre-multiplication of a matrix spews out an m by 1 vector. So that means the codomain should be represented as a linear combination of m elements. All right? So ibig sabihin, dahil ang result ng matrix vector multiplication ay 3 by 1, so ay 2 by 1, so dapat yung elements ng codomain ay may express mo sa linear combination of two elements. But that is precisely the definition of the dimension of W, right? How many vectors are there in a basis for W? So that means we choose the dimension of W to be equal to 2, which tells us that the number of rows always gives us the dimension of the codomain. And for simplicity's sake, I chose to illustrate this example by choosing W to be R squared. And again, you could be fancy about it. You can pick any vector space of dimension 2, be it a abstract vector, an abstract vector space, or a vector space of purely numbers. All right. Then, moreover, to ease out the calculations, I will assume, or I will choose a canonical basis for both R3 and R1. And again, canonical basis or the standard basis, these are the bases consisting of n by 1 vectors, right, whose nth entry is equal to the unity of the field and 0 elsewhere. So halimbawa, si E1 para kay R3 ay 1, 0, 0. Si E2 para kay R3 ay 0, 1, 0. Si E3 para kay R3 ay 0, 0, 1. Okay? So, and we have seen in our first example last time that canonical bases are very convenient because there is no distinction between the coordinates and the actual vector itself. nakita natin kung meron kang vector, say 3, 2, 1, and you convert it with respect to the canonical basis, what you get back is 3, 2, 1. Because the vector 3, 2, 1 can be written as 3 times E1 plus 2 times E2 plus 1 times E3, right? And that's why they are called canonical bases, because they are the natural representation of vectors, okay? But again, sometimes canonical bases might be unstable, so we sometimes opt to use some other bases. So essentially, those choices of V, W, and canonical bases for ordered bases gives rise to the linear map L from R3 to R2. So remember that in order to define how L looks like, we can go into the matrix representation concept we adopted earlier. So para ma-describe ko si L, kailangan kong sabihin paano siya nag-a-act sa lahat ng elements ng domain, and how do I get the element of the range, all right? So that means let's start our calculations by taking advantage of what we learned from last time. We learned from last time that the image of a vector V under the mapping L is actually equal to the matrix representation times the coordinate vector, or the vector of coordinates, and then whatever the product is, we translate it back in terms of the second order basis. Okay? So if we have V1, V2, and V3 to be the vector from R3, since we chose the canonical basis, the coordinates of V with respect to canonical basis E1 is equal to V1, V2, and V3. Again, that's the advantage of choosing the canonical basis, all right? So plug it into here, we get this, and then we carry out the multiplication. But be careful, what we get in the matvec multiplication, I'm going to use matvec as a shorthand for matrix vector multiplication. So when I do the matvec multiplication, I'll get this guy. But remember that what we get out of the matvec operation is a set of coordinates, and hence the use of parentheses. Okay? And then, so if these are in parentheses, that means they are not the actual vectors we are looking for. So I need to convert it back as a linear combination of the elements of the ordered basis. Okay? And so, but fortunately, E2 was chosen to be the canonical basis for R2. Okay? So it means whatever your matrix whatever your coordinates are, they also serve as your actual vector, right? Kasi mangyayari lang naman, first element times E1, second element times E2. Sa R squared, ang E1 ay 1, 0. Oh, sorry, vector yan dapat. Si E2 ay 0, 1 lamang. And if you simplify, you get this guy. And we say this is the linear transformation, or this is a linear transformation, L, defined by the matrix A. Okay. Well, if you change your choice of ordered basis, you will get a different set of coordinates here, but you will eventually end up with the same vector representation for the actual image of L. Because again, any vector, any linear transformation has exactly one linear transformation with respect to the ordered basis, and vice versa. So every matrix will give rise to a unique linear transformation with respect to an ordered basis. Okay. All right. So yeah, I just continued on and say something about the canonical ordered basis. But is the conversion clear? I hope that's fine because I just gave you one example for it. Did I give one problem for that in the homework? Hindi, no? Parang ang problem ko lang ay pagkuha ng rank, pagkuha ng nullity, tapos pagko-convert from linear transformation to matrix. Probably we can, probably I can add one problem. Gusto nyo ba yun? Para practice na rin. Let's have problem number 3 in homework 5 to be a conversion from matrix onto the linear transformation. What do you think, guys? Or depende sa matrix na ibibigay ko later. Okay. Sige, dahil walang objection, I'll take your silence as a yes. Okay, let's come up with homework problem 3 later. Para rin may magawa kayo while waiting for module 5. Okay. Now, corollary 28 gives us a representation for the composition of two linear transformations. So we'll start with three vector spaces v, w, and y with appropriate dimensions n, m, and p respectively. And then we choose ordered bases b, d, and g for them respectively. And then we look at the composition M circle L, right? Remember, M circle L will be a map from what? From V to Y, tama? Such that M of V is equal to, sorry, not M of V, M circle L of V is equal to M of L of V, right? So let's see why is this well defined. L of V is an element of W, which happens to be the domain of M. And so M of a W is an element of Y. So this guy is an element of Y. So indeed, M circle L is a map from V to Y. And we have proven in the previous module that M circle L is also a linear transformation, provided that M and L are linear transformations. And so it must have also a matrix representation. But equation 59, or this theorem, corollary 28, gives us a nice way on how to find a matrix representation, all right? So you don't need to go through the definition of M circle L of V to be M L of V, because ideally, or the long cut for deriving the matrix representation is to find the matrix representation of L, compute the matrix representation of M, and then use the matrix representation in L in deriving the matrix representation for M, all right? But thankfully, this theorem does the work for us. It says that M circle L is actually represented by the product of the matrix representatives of M and L respectively. But you need to proceed with caution here that remember matrix multiplication is not commutative in general. So if you have matrix A times B, so here we're talking about matrix multiplication. This is not necessarily equal to B times A. This will only be true for specific conditions, but in general, AB is not equal to BA, even if A and B are matrices of the right dimensions, okay? So here, we need to be clear that you are prem-multiplying by the matrix representation of M, the matrix representation for L, okay? And this is actually, we have a hint of that because we also know that composition of functions is not commutative, right? So M circle L is not necessarily equal to L circle M. So it follows intuitively that the matrix representation should be taken, uh, we should be taking extra caution in finding the matrix representation because we don't want to mess up the ordering of the matrices, okay? So if you have a vector V, oh, actually, I think that's exactly what the proof is. So recall that, yeah, medyo shortcut na yung proof. I did not use the long version that I am referring to earlier. But here, so since L and M are linear transformations, then they will have their matrix representations, right? The thing is that L will act on, or the matrix representative of L will act on coordinates with respect to B, while the matrix representation for M will act on coordinates with respect to D. Okay, so this is the usual function value evaluation using their matrix representations. Okay. Now, if M is equal to LV, because remember, whenever we are computing M circle L, sulit na pala siya dito, we will assume that this is equal to some element of W, right? Because L has codomain W. So every image under L is an element of W. So we'll assume that L of V is equal to W. That doesn't lose any generality for the proof. And let's evaluate M circle L of B. By definition, the composition looks like this, okay? And then from our matrix representation for LV, we can write it this way, okay? Matrix representative times coordinates, then convert back to the codomain. All right. So this guy is what? Actually, this guy is an element of W. Tama? Kasi nag-convert na ako papunta doon sa actual vector space dahil dito sa superscript na to. So since this is an element of W, then this guy M will act on that actual vector, right? But instead of looking at the vector, instead of looking at applying the linear transformation M to the vector W in W, we can use the matrix representation again. For this time, we'll have the matrix representation for M. So kung kukomputing ko to, using the matrix representation, I'll get the next line. And let's see why. Matrix representation or evaluating functions using matrix representation is amounts to premultiplication by the matrix representative, okay? So premultiplication of a matrix representative to what? To the set of coordinates with respect to the chosen ordered basis. Kaya nawala yung superscript na D. Kasi di ba yung matrix multiplication mag-work siya sa coordinates, hindi sa actual vector. And the product of these two guys is a set of coordinates. So matrix times coordinates. And then since I'm looking for the actual function value, i-convert ko siya with respect to the ordered basis for y. And by commutativity of matrix multiplication, pardon the violation of the meta-axiom of ignorance, because I think we haven't talked about matrix multiplication, but let's assume facts from basic linear algebra classes para hindi na humaba yung isusulat ko ng mga theorems. So we'll assume properties for matrix addition, matrix multiplication, what else? Finding determinants, finding eigenvalues perhaps, but I'll put them into writing later. So here I used the associativity of matrix multiplication to group the two matrix representatives in the final product instead of the matrix representative applied to this product. And so we have seen here that the mapping M circle L is nothing more but a multiplication or premultiplication of the product of the matrix representatives to the set of coordinates for the domain element, and then converting the result back with respect to the ordered basis G. So thus we have proven that indeed the representation for M circle L is the product of the representative for M and L in that right order. Okay? Any questions so far? Okay. Or medyo inaantok na kayo kasi bad weather naman talaga today, especially to those here in Calabarzon or I think pati sa northern part ng Luzon, medyo malakas na rin ang ulan. And Calabarzon experienced magnitude 6.5 earthquake, 5.5 or 6.5 earlier this morning. So I hope you guys are safe and sound. Okay. Now, this striking equivalence that we have just established actually is the basis why linear algebra courses, especially in the undergraduate levels, are focused more on developing things for matrices. Kasi if you can do things on matrices, there is a natural extension from the set of matrices and their actions on n by 1 vectors into an action of a linear transformation from a vector space of dimension n to a vector space of dimension m. So that's why, kasi in the undergraduate level, they might not have the maturity yet to work with abstract vector spaces. So kaya sinisimulan siya, okay, these are tangible things. Kasi um, you're just doing operations on matrices. You are multiplying things. Pero para saan yung pagmumultiply mo ng matrices? Sasabihin ng mga estudyante nyo, hindi naman sila nakakakita ng matrices in real life. But the thing is that these matrices that they are working with in elementary linear algebra are just a representation of linear transformations that can act on very complicated and even more very abstract vector spaces. Of course, over your field F. So parang ngayon, mag-generalize na siya. Yung ginagawa natin sa matrices, pwede natin siyang gawin sa set of functions. Because the set of all functions with the right operations and the right scalar field is a vector space. So kung vector space yan, lahat ng properties ng matrices kaya kong extend sa mga functions that maps functions. And you know, in the real world, almost all phenomena are modeled by functions. Right? So kahit yung propagation of sound in nature, it is actually governed by some partial differential equations. The solutions to that partial differential equation form a vector space. And since meron kang vector space, meron kang ordered basis. So kaya mong makompute ano dapat yung ilalabas ng aking speaker in order to get the sound that I want in one place of the room and one place of the other. So napro-provide mo yung solution to that because the complicated action or operation that converts an input on a speaker towards the sound perceived by a receiver in some area of space actually can be modeled by a matrix. And then if you have a matrix, wala na akong problema dun sa complicated abstract things like functions, set of complex numbers, and so on. If I have a matrix, I can put it into MATLAB or any program, and then they will convert the inverse. They will solve a linear system, however big it is, and then I'll get my input to my loudspeaker. This also works for optics. This also works for heat flow. So for modeling weather, for modeling the stock price, right? So that's one. Siguro ito yung mahirap, how to deal with or how to show applications of things, especially for instance linear algebra, because linear algebra is a nice theoretical discourse. I mean, on its own, it has a very rich mathematical content and mathematical foundation, which I'm happy that some of you expressed hindi naman necessarily interest, but fascination about the subject. Na parang naglalaro lang tayo dito with the fixed set of rules. But if you are a person who loves to see applications, medyo mahirap ipakita yung application ng linear algebra because linear algebra is almost always a tool for studying various phenomena. And as a tool on its own, hindi kayang i-compress yung applications in yung applications or yung interesting applications in the course with this. So supposedly, sana merong special topics problem where we can see the applications of linear algebra into that particular field. Pero that's why I see, I really appreciate and idolize high school teachers or elementary teachers, how they are able to motivate students, especially at that young age, in order to look at math, which they can perceive to be very how do you call this? Very abstract or very hindi ko maalala yung gusto kong term. Parang parang hindi siya kailangan sa tunay na buhay. So yeah, hands down ako dun sa mga teachers that are able to make their students, especially the young ones, really motivated in doing math. Kahit na nabibigay lang natin an example, I say, I bought 3 bananas, 4 bananas, and then 5 apples, and so on. or if Mary can paint the room in 2 days and John can paint it in 3 days, how many days will it take them to complete the work if they will work together? So parang mga ganon, which student might seem to be very artificial. Yeah, that's the term I'm trying to look at. Parang artificial or masyadong contrived yung textbook problems, but yet you are still able to motivate your students. Pero kasi in the higher level, we are actually relying on students being interested in the math from the get-go, and then we'll just build up from that. So yeah. Okay, too much blabbering for this morning. So let's take a look at corollary 29. Yeah. So in corollary 29, this actually is a consequence of the fact that the mapping between hom of VW is to the set of all m by n matrices is an isomorphism. Kasi di ba dun sa equivalence theorem natin, I think it's theorem 27, okay, napakita natin na isomorphic, isomorphic ang hom VW over F kay set of all m by n matrices over F, right? So, and this equivalence is not just a bijective map. So kasi kung sinabi natin na bijection yung meron kay hom at saka kay m by n or kay m sub m by n, then all we can say is that they have exactly the same number of members. Okay? So if you have a bijection or a one-to-one correspondence, ibig sabihin lang kaya mong i-match yung isang element nung unang set dun sa pangalawang set, all you can conclude from that is magkasindami sila ng laman. Right? Yun yung sa bijection. But we have proven that the mapping between the set of all homomorphisms and the set of all m by n matrices is not just a bijective map, but it is also a linear transformation. And hence the theorem said it was an isomorphism. If you have a homomorphism, it tells us that the properties of your domain is preserved in the elements of the codomain. And since it's a bijection, that means it is just like as if we are relabeling the elements of the set of all homomorphisms and disguising them into an m by n matrix. And that's exactly what we did in the last two examples. We take a linear transformation and then we get a matrix representation. So it's just like we are disguising the linear transformation as a matrix. And in the last example, we did it the other way around. We disguised the matrix as a linear transformation. And since that mapping is not just bijective, so kung bijective sila, alam natin magkasing dami yung linear transformations at lahat ng m by n matrices. But there's a bonus. The mapping is a homomorphism. Okay, so ibig sabihin the properties of the vector space of all linear transformations is preserved exactly in the same manner as the properties of the vector space of all m by n matrices. And on top of the least of those properties is the dimension of the respective vector spaces. So that means since there is an isomorphism between the set of all homomorphisms and the set of all m by n matrices, they are not just equal in number, but they must also be equal in dimension. So magkasing dami yung basis elements nila. So in summary, corollary 29 is telling us that the dimension of the set of all homomorphisms is equal to the dimension of all m by n matrices. Okay. But what is the dimension of the set of all m by n matrices? Remember ang dimension, ang dimension ng m by n of f ay equals to m times n, all right? But we said n, the number of columns, correspond to the dimension of the domain. And then the number of rows correspond to the dimension of the codomain. And so this establishes that the dimension of the set of all homomorphisms is actually the product of the dimensions of the domain and the codomain. And if you will read the proof, you will see that the trick was to use the fact that the mapping is an isomorphism. And so this means that they will share the same dimensions, okay? And we have computed before the dimension of an m by n, or the vector space of all m by n matrices. That's m times n. Associativity of multiplication of real numbers, or not associativity, commutativity of multiplication of real numbers will give us n times m. But again, n is the dimension of v, m is the dimension of w, right? So it's a corollary which directly follows from the equivalence theorem. I think that that we had in theorem 27. Okay. All right. So questions. Okay pa naman? So we have seen the equivalence. We have seen, or we have realized that, oh, it's an isomorphism. So all the properties of the set of all linear transformations will have an analog property in the set of all m by n matrices. And one of the pivotal properties that we talked about in previous modules about linear transformations would be the rank and the nullity of linear transformations. So the rest of the module will talk about how to find the rank and the nullity of a matrix, which is probably what you are more accustomed to doing in linear algebra classes. Kasi, di ba, nagsisimula kayo sa matrices doon, tapos i-define nyo ano yung rank ng isang matrix and so on. Pero baligtad yung ginawa natin because we are on the graduate level, so we start with an abstract thing and we try to deduce properties or things that we have been seeing all our lives before, but giving them ano yung rigorous mathematics behind them, or what's the idea behind these things that work fascinatingly well for, say, matrices over R or matrices over C. Okay. So since we'll be targeting the analog property for the rank and the nullity, let's look at the kernel and the range of a linear transformation and how it relates to the kernel and the range of a matrix. Okay. Definition 9 simply defines the kernel of a matrix. So the kernel of a matrix, of an m by n matrix over the field of scalars f, is equal to the set of all vectors in f to the n, right? The set of all n by 1 vectors, x, which will have the 0 vector in fm if you do the premultiplication of a to x. Okay? So yung kernel ng isang matrix ay lahat ng n by 1 vector na pag pinrem-multiply mo ng matrix na yon, ang makukuha mo ay yung 0 vector. Okay? Then moreover, the range of a matrix is the set of all possible products, matrix vector products. So kunin mo lang lahat ng elements ng f to the n, i-multiply mo siya or i-pre-multiplyan mo siya ng matrix A, kunin mo lahat ng vector na yon, they will comprise the range of A. Okay? Clearly, the kernel is a subset of f to the n kasi ang candidates mo dyan, mga x's in f to the n, pero ano yung ax must be equal to the 0 vector. Hopefully you notice that this is very analogous to how we define the kernel of a linear map, right? Ang kernel ng isang linear map ay lahat ng element ng domain na ang image under the linear map ay yung 0 vector. Ang kernel ng isang matrix ay lahat ng m by 1 vector na pag pinrem-multiplyan mo ng A, ang sagot ay yung 0 vector from your codomain. Okay? And the same thing happens for the range. And then here I talk about how is the kernel of a matrix related to the kernel of a linear transformation. Okay, so let's take a look at that. So suppose X is an element of the kernel of phi L. Remember that phi L is the matrix representation of a linear transformation. Okay, so ito ay matrix na nagre-represent sa matrix transformation. kukuha ko ng isang element x mula dun sa kernel na yon. At tingnan ko ano yung characters, ano yung characterization na pwede kong makuha from that statement. Again, the nice thing, we don't know anything much about the kernel of a matrix, but its definition. So si X ay nasa kernel ng isang matrix phi L if and only if, hence the biconditional here, if and only if yung matrix times si X ay equal to 0 vector. Okay, that's fine. That's the very definition of being in the kernel. Now, since these two guys are equal, what do they represent? Ano yung represent itong phi L times X? Do you guys remember? What do I get when I multiply a matrix representative by a set of scalars? Actually, yung sagot in symbols ay nasa slide na. Pero how do we interpret this guy? Anybody? Ayaw nyo lang magsalita. So, but anyway, I hope you remember that if you multiply if you multiply a matrix or the matrix representative by a set of coordinates, then that means what you get is another set of coordinates. But this would be the set of coordinates of the image under L with respect to the ordered basis D. Perhaps it would be, it's important that I put the subscript PD here, because I'm talking about conversions from the to basis expansions. So ibig sabihin kung equal silang dalawa, pero left-hand side ay set of coordinates, right? So pwede kong i-treat yung right-hand side being equal to the left-hand side to be also a set of coordinates. So ito ay set of coordinates. I-convert ko siya doon sa vector space. So, but this guy, the right side, is equal to the left side, so I can do exactly the same thing to it. Treat it as a vector of coordinates, convert it back to the basis of the codomain, and they should remain to be equal with each other. And again, the basis for that is that basis expansions are unique, right? Kung meron kang vector space, any vector in the space can be written uniquely as a linear combination of the chosen basis, all right? Dahil equal yung dalawang coordinates, parehas na basis yung ginagamit ko. So the images after the conversion must be equal to each other, okay? But this guy is exactly L of V. For some vector V, maybe we should write that here, where V is equal to, actually, where V is equal to, or VB is equal to X. See, X, yung coordinates ni V with respect to the ordered basis B. So this guy reduces to L of V. Okay, kasi kinonvert ko siya into the vector space, so the abstract vector space. And then this guy, pag kinonvert ko to dun sa vector space, puro zero yung coordinate. If you have puro zero na coordinate, so ibig sabihin magkakaroon ka lang ng sum of zeros in the basis expansion. So what we get here would be the zero vector in the codomain. And this, remember, is the very definition of V being in the kernel of the linear transformation. Okay? And this series of implications that we have just discussed are all biconditional in nature. Biconditional siya. So if you start with this, you can get this, and end up with this. So that means X being in the kernel implies V is in the kernel. But it's a biconditional statement. So from here, there's an arrow above. Pwede tayo makapunta rito. Pero may back arrow din. So pwede akong magpunta doon sa argument sa taas. May back arrow din. So pwede kong gamitin yung implication na yon and end up with this conclusion. So this series of biconditionals also imply that if we have a V in the kernel of L, then X must be also in the kernel of the matrix representation. Where, of course, your X is the set of coordinates for V. Okay, this shows that the kernel of a linear map and its matrix representative are isomorphic to each other. So they are complete disguises of each other's kernel elements. Okay? And then you can do the same argument for the range. You just replace this by the range and then by the definition of the range, but you are guaranteed to get another isomorphism or another notion of isomorphism between the range of the matrix and the range of your linear map. So ibig sabihin, naka-disguise lang yung kernel at range ng isang linear transformation into elements of the kernel and the range of their respective matrix representatives. Okay? And if that is the case, then dapat ay related din yung range at yung yung rank at yung nullity ng matrix representation at ng linear transformation. Okay? And I think that's what I'll try to establish in the next few slides. So, but before that, let's go to definition 10. In definition 10, okay, we define what the column and the row rank are. So if you start with an m by n matrix, okay, and suppose that C1, C2, and Cn are vectors in Fm that are the columns of A. Kasi di ba dapat meron tayong m rows. Bawat C sub I ay isang column. So that means pag in-expand ko tong C1, ang itsura niya talaga ay C1, 1, C2, 1, C3, 1, hanggang CM1. So indeed, yung mga CIs, siya ay element ni FM. Kasi dapat magkaroon ng M na rows itong matrix A. And there would be N of them, okay? Kasi dapat N yung number of columns. And they are all coming from the field of scalars, which I hope you realize now why the importance or why the focus we had with fields in module 1. Kasi yung study natin ng vector spaces is now being reduced to study of matrices with entries coming from elements of a field. So at least we should have a rudimentary field theory. Dapat alam natin yung basic properties ng fields, which is hard probably for those who have first seen it here. But the properties are actually a bit familiar or a bit natural because we are very accustomed with the set of real numbers or the set of complex numbers, so you can treat them as just generalization of the properties of R and C. Okay? But anyway, you see now, ang paglalaroan na lang natin ay mga matrices na ang laman ay mula sa field. Pero as I promised, hindi na ako magbibigay ng gaanong abstract na field F. Usually C or R na lang yung gagamitin natin na field para dun sa matrices natin, right? So going back here, if A has column C1 to Cn, then the dimension of the span of C1 to Cn, actually I forgot the term span when I was writing the handouts, that's why, or the modules, that's why I stick to using curly L to the set of all linear combinations. Pero most linear algebra books nga pala use the term span of C1, C2, and Cn to note or to call the set of all linear transformations of elements of a set. So yung curly L of C1 to Cn natin, siya yung span ng C1 to Cn, which is the set of all linear combinations of elements of the set with regards to other books, right? So nawala sa isip ko yung term na span when I was writing this. That's why I have L here. Probably it would have been better if I started with span because you might be familiar with it. Okay, but we define the column rank of A to be the dimension of this vector space. Remember, an L of X for any set X dimension. That dimension is what we call the column rank of the matrix A. So you can think of the column rank, dimension siya ng C1, C2, o ng span ng C1, C2 until Cn. So you can think of the column rank to be the number of linearly independent columns of your matrix A. Kasi di ba, ang dimension na to, alam ko to be less than or equal to n. Kasi si n ay yung dimension ng siya yung dimension ni F, siya yung dimension ni F to the dimension ni f to the n. Alright? So kung siya yung dimension ni f to the n, ibig sabihin pwede kong bilangin kung ilan yung linearly independent columns ni A. So the number of linearly independent, or because actually the set of all linearly independent columns of your matrix will give you a basis for this vector space. But recall that the dimension is simply the number of basis elements for any basis. So that means pag nabilang ko na ilan yung linearly independent columns, then that means that would be the column rank, because it is exactly the dimension of the span of the columns. And then analogously, if R1 until Rm are n by 1 vectors, or 1 by n vectors, are the rows of A, then the row rank of A is the dimension of the rows. So kulang to. Kindly insert. This should be dimension ng L of that guy. All right. So titingnan natin yung vector space consisting of linear combinations of the rows, and then look for its dimension. But again, the dimension is the number of basis elements. But here we have already m candidates. So ibig sabihin, titingnan ko na lang which of the rows are linearly independent to each other. The number of those linearly independent rows, or actually those linearly independent rows, will form a basis for this space. And since it's a basis, I'll count the number of elements. That will be the row rank. So equivalently, the row rank is the number of linearly independent rows for your the rows of the matrix, linearly independent rows of the matrix. And I think that's what I mentioned here. Okay. And then theorem 30 is an important result from linear algebra. The proof is quite tedious mechanically, but the essence of the essence of this theorem actually is in the result itself and not in the proof. So you can read the proof from any linear algebra book, but our focus here is to appreciate the result itself. So it says here that if A is an m by n matrix, then its column and row rank are equal to each other. So it doesn't matter whether you look at the number of columns or the number of rows that are linearly independent, you'll get the same number. And that number is guaranteed to be less than or equal to the minimum between the number of rows and the number of columns. And probably let's investigate this, why that inequality is true. Because remember, okay, column rank is the number of linearly independent columns, all right? But the elements, or each of the columns, is an m by 1 vector, right? Bawat isang column ay element ni f to the m. Pero ano ba ang dimension ni f to the m? Ang dimension ni f to the m ay m. Kasi ang isang basis para kay fm ay yung mga elementary basis, right? So ibig sabihin si fm ay dimension m. So this guy is a subset of f to the m. Kasi ang mga elements yan nanggagaling sa fm. So ang dimension nitong vector space na to ay hindi dapat mas malaki sa dimension ng parent vector space. So that means that this guy is less than m, being the dimension of dimension of the vector space where the CIs are coming from. And so the column rank has dimension less than or equal to m. And similarly, let me check that. Yeah, that's right. And similarly, each of the rows is an element of f to the n, but the dimension of f to the n is equal to n. So that means the row rank cannot be greater than n. Theorem 30, the first part, tells us that the column and the row rank are equal to each other. Pero yung column rank ay dapat mas maliit or equal sa m, yung row rank mas maliit or equal sa n, so therefore their common value must be less than the smaller number between m and n. So kung meron kang m by n matrix, kunin mo ano yung mas malaki, number of rows, number of columns. Kung alin yung kung alin yung mas maliit, siya yung magiging maximum possible value for the column and the row rank. Kasi yung column and row rank are equal to each other. Okay? And so another nice consequence of theorem 30 tells us it doesn't matter whether you look for or you look at the column rank or the row rank, you'll get the same number. So why bother calling them by different names? Or why not unify the notion of a rank for a matrix? And that's what the next remark here tells us. Since the row rank and the column rank are equal to each other, then let's call the rank of A to be the common value. And let's denote it by rank A. Okay, so ibig sabihin ang rank ng isang matrix ay kung ilan ang linearly independent columns or ilan ang linearly independent rows. So bahala na kayong pumili. Ano kaya yung madaling i-check kung linearly independent? Yung rows ba or yung columns? Because either way, you'll get the same value because you'll be getting the row and the column rank. So, and they are equal to each other. And that common value is what we call the rank of a matrix. And then now we're ready for theorem 31, which is the nice consequence of the isomorphism between the set of all homomorphisms and the set of all m by n matrices. Because the rank of a linear transformation is equal to the rank of its matrix representative. So, di ba yung rank, siya yung range, dimension ng range ng isang linear transformation. Tapos sabi natin dati, mahirap hanapin yung range ng isang linear transformation. Much more is to look for the dimension of the range. And that is especially difficult if the codomain is a very abstract vector space. Mahirap imagine kung abstract yung vector space. But mathematicians found a way how to get a nicer way of computing the rank of a linear transformation. Instead of dealing with abstract vector spaces, the complicated domains and codomains of linear transformations, then they were able to reduce the idea of the rank of a linear transformation to the rank of the matrix representation. Which is nice because if you have just a matrix, you can count, or it would be easy to count how many linearly independent rows are there or how many linearly independent columns are there. Okay. Now, I did not include the proof, but the proof relies on the isomorphism between the set of all linear transformations and the set of all matrices plus the very definition of the rank and the equivalence we have discussed earlier. So pwede nyo i-compile yon into a proof. Okay? Okay. Now, next notion is full rank. We say that the matrix is a full rank if and only if the rank is exactly equal to the smaller between the number of rows and the number of columns. Remember, we said that the rank is always smaller than the minimum between m and n. Okay? But if so happened that a matrix A attained the highest possible rank, nakuha niya yung pinakamataas na rank, which is the minimum between m and n, kung ano yung mas maunti sa rows or columns, then we say A is a full rank. Okay? So full rank siya kapag ka ang rank niya ay yung pinakamalaking posibleng rank ng isang m by n matrix, which is the minimum between the number of rows and the number of columns. And then theorem 32 gives a nice characterization of a matrix of full rank. So some books might use theorem 32 as a definition for a full rank matrix. And this guy will serve as a theorem. Pero sa atin baliktad, we develop it using full rank as having attained the maximum rank. Kasi mas parang natural na i-define yung full rank ng ganon. Full rank siya pag nakuha niya yung pinakamataas na rango, which is the minimum between m and n. So easier to remember.
And then theorem 32 is viewed as a consequence. If you have a matrix of full rank, then kapag ka si x ay hindi equal kay y, then ang ax is not equal to ay. So what does this statement remind you of? Can you restate what that statement means, or how can we say that statement in another way?
To one correspondence po. X is not equal to y, then f of x is not equal to f of y.
Yes, that's right, Jeg. Pero correct ko lang ng konti, huwag mong isama yung correspondence. Just say it one-to-one. Kasi pag sinabi mong one-to-one correspondence, siya ay parehong one-to-one and onto. So, yeah, you're correct though. The idea is correct. The matrix A is one-to-one. Meaning, if you have two elements that are not equal to each other, then prem-multiplication of the matrix A will not make them equal to each other. Or siguro mas familiar tayo dun sa contrapositive. So the contrapositive is, I think that's what we used before. This is equivalent to saying that ax equals ay implies x equals y. So this is what we call the contrapositive of the statement, which is equivalent to the statement itself. So whenever you want to prove something is one-to-one or something is monic, then you can either start with x not being equal to y and show that ax is not equal to ay, or use the contrapositive, start with the assumption that ax is equal to ay and show that x is not equal to y. Either way, that's a nice proof for showing that A is monic. Okay? So that's one consequence of being full rank. Pag full rank, hindi pwedeng magkaibang vectors ay parehas yung product with A. Okay? And the proof is here, but I'll set that as your reading assignment. I think I included most of the details here. So I'll skip that so that we'll have more time to look at the other consequences, which would be helpful in doing homework 5 or the first two problems of homework 5. Okay. Definition 11. The nullity of a matrix A is the dimension of its kernel. So basically, gagayahin ko lang yung ginawa natin sa rank. Though hindi ko na pinakita yung details, I just showed you the results of a similar analysis as what we did with the rank. So first we define what the nullity of a matrix is. The nullity of a matrix is the dimension of its kernel. And so again, by the equivalence of the set of all homomorphisms and the set of all m by n matrices, we can say that we can prove theorem 33, which tells us that the nullity of a matrix is equal to the nullity of its matrix representation. And obviously, since elements of the elements of the kernel are coming from the domain of both the matrix and the vectors and of the linear transformation, parehas na dimension n yung pinanggagalingan ng kernel elements. So that means the nullity of both the kernel of the matrix, the nullity of the matrix and the nullity of the linear transformation must be less than or equal to the dimension of L. Actually, something is wrong here. This should be nullity of L. Sorry about that. Kindly correct. So theorem 33, please correct it. The statement should be null of L is equal to the nullity of phi L. So yung nullity ng linear transformation L ay equals sa nullity ng matrix representation niya, which we call to be phi L, ay less than or equal siya sa dimension nung domain. All right? And then hopefully, final result na to for the day, the Rantality Theorem for matrices. I called it a corollary 34, because it will follow from the Rantality Theorem for abstract vector spaces that we had before, and then using Theorem 33 and using Theorem 32. Theorem 31. So, ibig sabihin kasi, magsimula ka sa Rantality Theorem para sa linear transformations, right? Sabi natin doon, ang rank ng L plus null ng L ay equal kay dimension ng domain from the Rantality Theorem for abstract vector spaces. But from theorems 31 and 32, ang rank ng L ay equal sa rank ng matrix. Nullity ng L ay equal sa nullity ng matrix representation niya. So, ibig sabihin, the sum of the rank and the nullity of your matrix must be equal to the dimension of V. Pero sabi natin yung dimension of V ay laging equal sa number of columns. So that means it must be equal to n. So again, you can choose whether you want to look at the dimension of the kernel of a matrix or look at its rank. Tapos from there, just compute one of them, subtract it from the number of columns, you'll get the other one, right? So I think for the rest of the module, I computed the rank. So gagamit kayo ng Rantality Theorem para makuha yung nullity. So nullity is equal to n minus rank. Mako-compute natin yung rank using a nice algorithm. So makuha yung number na yon, subtract it from the number of columns of the matrix, then you're good. You can find the nullity. Okay. Now, how do we find the rank exactly? That's what okay. That's why I need to recall here elementary row operations. So show of hands, sino yung familiar pa rin with elementary row operations? Or kinalimutan nyo na talaga siya? Okay, good. Jeng, who else? Okay, I'll assume na ayaw nyo lang magtaas ng kamay. But anyway, these are elementary row operations. May tatlong elementary row operations. Number one, if you have a matrix, interchanging any two rows of the matrix is an elementary row operation. Multiplying any row by a non-zero constant is also an elementary row operation. And the last elementary row operation is adding a multiple of a row to another row. Okay. So usually these operations are used repetitively and in succession to express the matrix A into what we call the reduced row echelon form. So yung reduced row echelon form, for brevity, let's call it RREF of a matrix, is the matrix satisfying the conditions in definition 12. Okay? So i-denote natin by RREF of A, yung matrix na makukuha ko after doing operations that will give the reduced row echelon form. All right? Sir Edward, do you have a question? Or ito yung para sa ano kanina? Yung sa quick survey.
Yes, sir, yan.
Okay. All right. Thank you. So, pagkuha ng RREF. So, ano yung condition para masabi na isang matrix ay nasa reduced row echelon form na? Number one, lahat ng zero rows ay nasa pinakailalim ng matrix. So kung sa matrix nyo may nakita kayo na row of 0, ilipat nyo na kagad siya dun sa bottom. And that's fine because interchanging rows or swapping rows is an elementary row operation. Okay? Second, the first non-zero entry in each row, unang non-zero entry in each row, we'll call it the leading entry. The leading entry should be 1. Okay, lahat ng leading entries should be equal to 1. Condition 3, the leading entry in a row is strictly on the right of the leading entry of the row above it. So kung meron kang matrix, meron kang leading entry dito. Huwag natin nung ilagay. Okay. Baka ito yung first row. So, ang leading entry niya ay 1. Required lagi yan para sa RREF. So, nandito siya. So, lahat ng leading entries to rows na nasa ilalim ng first row cannot be here, or cannot be here. Kasi kailangan yung leading entries sa mga mas mabababang rows ay nasa kanan palagi no leading entry nung nasa ibabaw. So at most, the leading entry in the second row could be here. And then the leading entry in the third row could be here. And since the leading entry must be 1, that's the first non-zero element. So dapat ganito yung itsura ng matrix, right? So yun yung sinasabi ng condition 3. Dapat lahat ng leading entry sa mga rows na nasa baba ay nasa kanan ng leading entry dun sa taas. Okay? And then the fourth condition, bawat column na may leading entry ay dapat 0 na ang laman sa lahat. So, if you have here, so don't worry kung medyo mabilis yung examples dito kasi makakita naman tayo mamaya ng RREF in details. Pero since this is 0, 0, 1, 2, 3, 5, 6, alright? So, ibig sabihin lahat dapat na nandito ay 0 na. Kasi leading entry to, dapat 0 na yung nasa ilalim niya. And then, bawal magka-leading entry dun sa nasa unahan, so puro 0 na yon. Okay? Kung meron ako leading entry dito, sa third row, dapat lahat ng laman sa column na yon ay puro zeros dapat. So that means this is not in RREF kasi may 3 ako dito. Dapat ito maging 0 para masabing RREF siya. Bakit? Kasi dapat yung column na may lamang leading entry dapat ay walang non-zero element other than the unity or other than itself. May leading entry ka na dito, puro zeros na dapat yung nasa taas at nasa baba. Okay? So that's how we get, those are the criteria for checking if your matrix is in reduced row echelon form. A result in linear algebra tells us na unique dapat yung RREF ng isang matrix. So kaya nagsettle ako to use RREF because we could have used simply the row echelon form. Pero kasi hindi unique yung row echelon form. So para uniform yung makuha nating results, I opted to use RREF in our discussions. Pero some of the results here can be, the conditions of some of the results here could be made less restrictive. Instead of RREF, we can use the reduced row, the row echelon form lang. But never mind about that. Let's focus on RREF. And let's take a look at example 54. And the challenge here is to find the RREF of A. So again, to find the RREF, we need to perform elementary row operations. Para yung definition 12, lahat ng conditions on definition 12 ay masatisfy. Okay? So here we start with the matrix A. So hindi nagma-matter yung ordering. You can swap the ordering. You can pick which one you want to put on top and so on. So yeah, pwedeng magbalik-baliktad yung ordering ng EROs or elementary row operations, pero in the end we'll get the same matrix because RREF is unique. Okay. Now nakita ko ay okay. So marami itong zeros. So, ibig sabihin, hindi siya pwedeng nasa taas. Kasi di ba pag ito na yung gagawin kong leading entry niya, dapat 0 na lahat ng nasa column na yon. So, hindi to pwedeng magstay sa taas. Kasi pag nagstay siya sa taas, pwede ko itong gawing leading entry. So, mafo-force na 0 na yung mga nasa baba. Tapos, lahat dapat, di ba, ng leading entries ay nasa kanan niya. So, hindi ko pwedeng i-stay to sa taas kasi wala na akong paglalagyan ng leading entries ng dalawang rows kasi dapat nasa kanan siya nung nasa ibabaw. So that's why I was forced to do as my first ERO, the interchanging or the swapping of the first and the third rows. So pag ginamit ko itong notation na ito, ibig sabihin si R1 at si R2 pinagbaligtad ko lang. R1 and R3 pinagbaligtad ko lang. So that's why I put the third row as my first row. So there we go. And then the first row became the third row. Okay? And then remember, the leading entry should be equal to 1. So, but the leading entry in the matrix that we have so far is 1/3. But I can easily multiply the first row by 3 to make its leading coefficient equal to 1. Okay? That's why the second operation I chose is to multiply the first row by 3. So yung notation ko si R1, papalitan ko lang ng 3 times R1. And that's how I get 160. All 2 rows are retained. ginagawa ko one ERO lang per line para mas makita natin yung detalye. Okay? Now, at this point, we know that this is our leading entry for the first row. So one of the conditions in definition 12, wala na dapat non-zero element sa ilalim niya. Because if your column contains a leading entry, then all entries other than the leading one should be equal to 0. So I need to force the issue that this is 0 and this is 0. Luckily, I don't have to do anything about the third row. So I'll just need to take a look at the first row. Oh, sorry, the second row. But one ERO, or I'm using ERO for elementary row operation, is to add a scalar multiple of one row to the other. So I want to make this equal to 0, but this is exactly the one on top. So what I can do is to replace the second row by the second row minus the first row. So pwede nyo yung kopyahin yung hindi maapektuhan na row. Row 1 will not be affected. Row 3 will not be affected. But row 2 will be changed to R2 minus R1. Remember, subtraction is just addition by the inverse. So technically, addition pa rin to. So ERO pa rin siya. So R2 minus R1, so that gave us the 0. 5 minus 6, negative 1, negative 2 minus 0, we get negative 2. All right? And then it looks like that this guy should be the leading entry for the second row. But remember, the condition is that the second row must have a leading one. All right? So how do I make it 1? Well, I can just multiply the second row by negative 1 and do the replacement. So I copy the first and the third columns because they are not affected. I'll change the second row by the negative of the second row from above. So in-negate ko lang, 0 became 0, negative 1 became 1, negative 2 became 2. And then I retain 0, 0, 3. Okay? And then, ano pa yung usapan natin? Oh, it seems that this guy should be changed to 1 because it serves as a leading entry for the third row. Okay? So since this must be the leading entry in the third row, I need to change the third row into 1/3 of the original row. So i-multiply ko lang lahat ng 1/3, I'll get this guy. Okay? Pero ito pala yung nakalimutan kong gawin muna. Ito yung mas natural gawin. Late ko na-realize na at this point pala, may leading entry na ako dito na 1, pero may 6 pa rin ako doon. So before I continue, I need to remedy that problem. Leading entry dito, this must be 0. So I need to replace the first row kasi yung form niya ay hindi magsasatisfy sa RREF. I'm going to change the first row through an ERO. Hindi na ako pwedeng mag-multiply by a scalar. Kasi pag nag-multiply ako ng scalar, mamumultiply din yung leading entry, hindi na siya magiging 1. So the remedy is to add a multiple of a previous row or by another row to this given row. Okay? So para mawala yung 6 doon, pwede kong gawin R1 minus 6R2. At yun yung maganda kung bakit dapat na 0 nyo na yung mga nasa ilalim ng leading entry. Para pag nag-add ka ng isang scalar multiple ng isang lower row sa isang upper row, hindi maapektuhan yung leading entry. Kasi laging 0 naman yung ma-add, multiple lang ni 0 yung ma-add sa kanya or masusubtract. And you'll see that here, that even if I added a negative 6R2 into R1, ano nangyari? 1 minus 6 times 0? 1 minus 6 times 0? Baliktad. Ano yung ginagawa ko? Dapat meron akong 1 minus 6 times 0 that gave me 1, which I want. I want to retain the leading one there. But here, this caused the problem, but see, 6 minus 6 times 1, that will be 0. And then 0 minus 6 times 2, you'll get the negative 12. And since we are just changing the first row, copy ko lang yung second and third rows. Alright? And then ano pa yung problema? Oh, meron ako leading entry dito. So dapat lahat nung nasa third column ay magiging 0 except for this one. Kasi if you have a leading entry, all entries in that column or all other entries in that column must be equal to 0. So kailangan ko itong i-0, kailangan ko itong i-0. Pero magagamit ko na yung third row kasi 0, 0 to, hindi nila maapektuhan itong mga entries na to. So if I'll do R2 first, I can replace R2 by R2 minus 2R3. So R2 minus twice R3, 0 minus 0, that gave the 0. 1 minus 2 times 0, that retained the 1 there, which is what we want to happen. And this is the crucial thing, 2 minus 2 times 1, so that's 2 minus 2, 2, we get the 0. Okay? And then we'll do that finally for the first row kasi problema pa rin natin yung 12, negative 12 doon. May 0 ka na, may leading entry ka na dito, so dapat ito mag-0. But again, I can use the third row, or that's the ideal scenario. I'll use the third row kasi if I multiply the third row by anything and add it to the first row, etong dalawang ito ay hindi na mababago kasi 0 na yung mga nasa columns na yon. Right? So in particular, I can replace R1 by R1 plus 12R3. Okay, so that means R1 plus 12 times 0, that's, oops, may mali, sorry about that. 1 to dapat, alright? Kasi magiging 1 plus 12 times R3, so that's going to be 1. 0 plus 12 times 0, that is 0. Then negative 12 plus 12, that will give us 0. Alright? And you can check all the conditions of definition 12 are met. So we can say that the RREF of A is equal to the 3 by 3 identity matrix. By the way, from now on, if you see an I sub something in the context of matrices, so this I sub n would be the n by n identity matrix. N by n identity matrix because it will contain all 1 on the diagonals and on the diagonal and 0 elsewhere. But this is called identity matrix because it is the identity with respect to matrix multiplication. Right? Hindi siya dahil additive identity siya dun sa vector space, pero kasi siya yung identity with respect to matrix multiplication. Okay? So, I don't know, I believe in one point or the other, na-meet nyo na yung pagko-compute ng RREF. Sometimes it takes getting used to it. Pero para ka naglalaro ng puzzle. Paano mo masasatisfy lahat ng condition, ng definition, with a certain set of rules para lang makuha yung RREF form. So I just included one example here because I think you could have, or you have encountered this before. But if that was years ago, probably you need to take some practice. And okay lang yan, magbigay kayo ng, kung gusto nyo mag-practice, magbigay lang kayo ng kahit anong matrix. Make up your own matrix. But do not make it too large a matrix. Kasi masyadong dadami yung i-compute nyo. Tapos ipa-RREF nyo kay MATLAB para ma-check nyo yung final answer nyo kung tama. Okay? Alright, so yeah, I have some theorems here. Pero hindi naman siya ganon, at least theorem 35.1 is not that big a deal. But I just want you to learn, kung hindi nyo pa alam, parang trivia lang yung 35.1, na kung si B ay na-obtain nyo from A using elementary row operations, actually, sorry, hindi pala siya yung gusto kong trivia. Yung elementary row operations ay nangyayari. It is not just a lexicographic operation. Hindi lang siya naglilipat ka ng rows, naglilipat ng columns, nagmo-multiply ng scalar, or nag-a-add ng rows to another on its face. Technically, what happens there is that you are pre-multiplying by an elementary matrix. So for instance, meron ka matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Gusto mo after RREF maging 4, 5, 6, 1, 2, 3, 7, 8, 9 siya, which is possible via ERO. Pero yung ERO hindi lang siya lexicographic na operation in the sense na hindi mo lang talaga pinagpapalit yung nakikita mong characters. Meron siyang underlying matrix operation. And for that, this is a pre-multiplication by an elementary matrix. What is an elementary matrix? It is a matrix obtained from the identity na kung saan ginawa mo yung gusto mo mangyari dun sa matrix, dun din sa identity. Magulo, pero dahil gusto kong iswap yung first and second row, ang ipang pre-multiply ko sa matrix na to ay identity, pero pinag-swap ko intended rows ko. Alright? So when you do this times this, you'll get this guy. Okay. So parang kung anong gusto mong mangyari dun sa RREF, kung sa identity matrix, so i-rearrange mo yung rows ng identity matrix, i-multiply mo yung row ng identity matrix, or i-add mo yung isang row ng identity matrix to the another matrix, you'll get what we call an elementary matrix. And if you multiply the elementary matrix with a matrix M, you'll get a result using the elementary row operations. So hindi lang superficial yung elementary row operations, meron siyang matrix operation involved, right? And with that, probably it's easier to realize theorems 30, parts of theorem 35, hindi nagbabago. Sorry, hold on, excuse me. Okay. Hindi nagbabago yung vector space spanned by performing elementary row operations. Okay. So if B is obtained from A using elementary row operations, then A and B will have the same vector spaces, right? Or they will generate the same vector spaces. And the highlight would be theorem 35.2. The non-zero rows of REF of A are linearly independent. And in particular, rank A is the number of non-zero rows of RREF of A. So ang rows ng matrix RREF ni matrix A ay laging linearly independent. So that means the dimension of the row space of A is equal to actually the rank of A. Kasi kung ilan yung linearly independent rows, yun yung rank niya. Tama? So that means rank A is nothing more but the number of non-zero rows of RREF of A. So the very mechanical thing that we performed earlier, which is basically using EROs to come up with the RREF, actually has a more theoretical purpose or significance, because it's not just a puzzle that we can do on our free time, but it allows us to compute the rank of a matrix by just counting the number of non-zero rows of the RREF. And more than that, it's more profound when you think about the matrices representing linear transformations. We said it's quite a daunting task to talk about finding the range of a linear transformation, much more to find the dimension of the range, which will give us the rank of the linear transformation. But based on our discussions today, we have found a mechanical way on how to find the rank of a very abstract thing, such as a linear transformation. Just perform EROs to get the RREF of a matrix. Count the number of non-zero rows, then we're done. Okay. Now, let's see a quick example here. Hindi rin pala ako nakapagpigil. Sinulat ko rin about yung EROs being pre-multiplication by an elementary matrix. Okay. By the way, you can also do elementary column operations. So lahat lang ng rows sa definition ng ERO, palitan nyo lang ng columns. That can lead you to finding the reduced column echelon form. So At definition ng RCEF ay RREF din, papalitan nyo lang lahat ng rows by the columns. And then the number of linearly independent columns in the RCEF of a matrix will also be equal to the rank of the matrix. Though mas sanay tayo sa RREF. Kasi anyway, parehas lang naman yung makukompute natin coming from RREF or RCEF. Or parehas lang makukuha nating number of non-zero rows or non-zero columns. Though yung RCEF and RREF of a matrix might be different from each other, pero be guaranteed that the number of non-zero rows and non-zero columns for the RREF and the RCEF are respectively equal. Okay. So let's see this in action. The previous discussions that we have, and probably we can stop here. Example 55. We want to find the rank and the nullity of this matrix A here. Again, I'm going to play with RREF here by using EROs. Pero para mas simple yung discussion, hindi ko na ipapakita yung yung EROs as pre-multiplication by an elementary matrix. Ang gagawin ko na lang, gagawin ko yung lexicographic perspective ng EROs. Oh, by the way, para makuha yung RCEF, kailangan yung gawin yung elementary column operations. So, kaya talaga magkaiba. Malaking chance na magkaiba yung matrices na makukuha nyo. For the RREF, yes.
Sir, but you can always use the transpose, right? So, you just use the transpose, then do RREF instead of RCEF.
Yes, that's right. Though, sa purposes natin, ginagamit lang natin yung RREF at saka yung RREF pagkuha ng rank. Pero you're right, in some applications, yeah, you want to jump from RREF to RCEF and vice versa, but you're right, they are just transposes of each other, right? Okay, so kung mas familiar kayo with RCEF, then that's fine. Though I'll stick with RREF. So here, starting matrix A, and then may panggulo kagad dito na 2 because I'm planning this to be my leading entry for the first row. So what I'll do is to replace the second row by the second row plus twice the first row. So that means 2 plus -2, that will give us a 0. 0 plus 2 times 0, that's going to be a 0. 2 plus 2 times -1, that's 2 times -2, or plus -2, that's going to be 0, and so on. Okay, and then I'll copy the third row. Okay, and again, first problem here. Time screen ko, sorry about that, but yeah, and then you will continue on doing this. Actually, mabilis lang pala siya. Okay, so do you guys need do you want us to go into the details? But I guess you can trace it on your own. Mechanical lang naman yan, so you can verify that indeed you'll get here as your RREF. Leading entry 1, leading entry here. Lahat ng leading entry ay nasa kanan, nasa ibabaw, that's fine. I have a leading entry here, kaya 0 na lahat na nasa ilalim niya. I have a leading entry here. Hindi pa pala to RREF, sorry about that. Kasi leading entry to, so dapat ito ay mag-0 din. Pati na lang chinek natin. So that means I need to change what? I need to change R1 into R1 minus twice ng R2. Tama ba? So magiging 1 minus 0. So that's going to be 1. 0 minus 0. 1 minus 0. So that's going to be a 1. And then 2 minus 2. So that's going to be a 0. Then 0, 0, 0, 1. And then 0, oops. 0, 0, 0, 0. Okay? So dapat pala ito ay 0. that ano? Okay, so I think this is the right REF. Kindly correct your notes again. So theorem 35.2, we know that the rank of the matrix A is the number of non-zero rows. We only have one zero row in the RREF, so that means that the rank of A is equal to 2. Okay? And to find the nullity, I can just appeal to the Rantality Theorem. The null of A is the number of columns minus the rank of A. So it's going to be 4 number of columns minus the rank, which we computed as the number of rows, the number of non-zero rows of the RREF. Subtract them from each other, we get 2. So the rank of the matrix is 2, the nullity of the matrix is 2. So that means that the rank and the nullity of the matrix of the linear transformation represented by A are 2 and 2 respectively. Okay. Now I have example 56 here, another example. Oh, this is a quick one in which you can do inspection. You don't need to do RREF all the time, because if you have only two rows, for instance, you can check na 111 is not a scalar multiple of 2, 3, 4, 5, or the other way around. Kasi lahat ng scalar multiple ni 111 ay laging magkakaparehas yung components. So that means 2, 3, 4, 5 cannot be written as a scalar multiple of 1111. That means this row and this row are linearly independent, and so that the rank of A is equal to 2. Okay? Kasi yun yung number of linearly independent rows. So that's equal to 2, or actually, ginamit ko pala dito yung isang theorem which says that kapag actually, let me rethink the statement I put here. Anong sabi ko dyan? Note that the rows of A are not scalar multiple of each other, which is true. Thus, the rows are linearly independent. So if the rows are linearly independent, then A is a full rank. Yun ba yung nasa theorem natin? A is, if the rows are linearly independent, then A is a full rank. Let me check that later, but the result is correct, but I want to make sure that I stated this theorem para mag-make sense yung susunod na discussion. All right? So because the rows are linearly independent, then from above, or in case I forgot to put that theorem, I'm going to replace this paragraph with something more natural. So si A ay full rank, at sabi natin pag full rank siya, ibig sabihin ma-attain niya yung pinakamataas na rank, which is the minimum between M and N. There are 2 rows, 4 columns, minimum is 2, so the rank is 2. Or you can, I think the easier way to interpret this is that we have 2 linearly independent rows, and so that the row space or the columns, sorry, the dimension of the span of the rows is equal to 2, because 111, 2, 3, 4, 5 will serve as a basis for the span of the rows of A. At dahil siya ay basis, ibig sabihin siya rin yung dimension ng row space. So it would be the row rank. The row rank would be equal to 2, but the row rank is always equal to the rank, so the rank is equal to 2. So it tells us there are multiple ways on how to attack a certain problem, depende kung anong theorem yung nabigay or anong theorem yung natandaan nyo. But of course, theorems with names are extra important, and so let's use them, take advantage of them. So the Rantality Theorem tells us that the nullity is number of columns minus rank. So we'll have nullity is equal to 2. All right. And then the rest of the examples are MATLAB codes. Maybe I can go through them quickly. Sorry kung medyo mahaba uli yung meeting today. I'll just try to finish it. So kung medyo fatigue na, you can stop and then just watch the recording at a time more convenient to you. Oh, by the way, guys, automatic pala yung recording sa Teams. Once the meeting is ended, it will just take a couple of minutes for the recording to be up. So makikita niyo siya dun sa thread or dun sa conversation thread natin about this class meeting. In one of the comments, you'll see there the video recording. So you don't need to wait until me to wait for me to share the link because you can access it via UP's OneDrive. Medyo dinidelay ko lang siya para na-download ko na siya and na-upload ko na siya sa channel ko bago ko i-share yung link para isang message na lang. But again, you can watch the recording via your via SharePoint or via MS Teams. Okay. Now I opt to always keep a personal copy of the video recordings of my classes and put it somewhere in the web para once, for instance, you graduate, you might not have access to UP's resources like Teams and SharePoint. So that's why I always upload it into a third-party server. It just happened to be YouTube, which is madaling mag-upload, walang data cap, at saka I think it's accessible to all. And then what I plan to do at the end of the semester, I'll put up a web page in my website about this class. I'll compile there all the resources so that if you remember us discussing something that is relevant to your research, you can access it even if you're not connected with UP anymore. So yeah. Okay. But anyway, example 57 teaches us how to code this in MATLAB. MATLAB has a nice command for finding the RREF because imagine if you have if you have a matrix with 50,000 rows and 10,000 columns, and believe me, if you're doing applied research, you will be dealing with them. I used 100,000 by 100,000 matrix, and it would be nearly impossible for me to do the RREF by hand, or if I will solve a linear system involving that matrix. So that's why we can't take advantage of computing resources. And MATLAB in particular has a one-line command that will compute the reduced row echelon form of a matrix A. So if you type B equals RREFA, of course, wala dapat yung period. Yung period dito ay para dun sa sentence ko. Pero sa command, ito lang, RREFA. Again, in MATLAB, if you just encode this, of course, kailangan yung i-declare ano yung matrix A. Pag meron ka ng matrix A dito, na-define mo na siya sa taas, then call B equals RREFA, it will compute for the reduced row echelon of A and save that in the variable B. So elsewhere in your code sa ilalim, pag naglagay ka ng B, ito yung gagamitin niyang value. Gagamitin niya yung value ng RREF ni A. Okay? And then you can find RREF, count the number of non-zero rows, and then you're good. You can find the rank. But MATLAB does something even better. It can give us the rank right away. So you define the rank A on top, encode rank A, store it to a variable R. This will give us the rank of the matrix. Doesn't need to look for the RREF anymore. No need to count the number of non-zero rows, but automatically we get the rank. Okay. And then also better is that MATLAB can provide us a basis for the null space or for the kernel of the matrix A. Okay. So that's what MATLAB calls the null of A. Though medyo magkaiba na tayo ng notation with MATLAB because our null of A is the nullity of ang ating null A ay nullity ni matrix A. So ibig sabihin ito ay natural number. Right? Number of basis elements ng kernel ni matrix A. But in MATLAB, if you ask it to find null A, it will give you a matrix. A matrix whose columns are form a basis for the kernel of A. So makita nyo mamaya, bibigyan nyo yung mga columns, it will give us a basis for the null space. And if you count the number of columns, that will give you the nullity. Kasi bawat column ay isang basis element para sa kernel. So the number of elements in the basis, which is the number of columns in Z, would be the nullity of our vector of the kernel. Sorry, the nullity of the matrix A. which is the dimension of the kernel. And then just quickly, let's browse through the code. I think we already looked at this last time, but in passing. So tingnan natin siya ngayon. Have you guys tried using MATLAB already? Any problems? Did you encounter any problem? I didn't get any message about MATLAB, so I think okay naman, or I assume okay naman. Don't hesitate to tell me if there's a problem. If you do not have a computer or a machine that you can use to run MATLAB, it's perfectly fine. Just let me know, okay? So that I can exempt you from doing the MATLAB exercises. But I need to know, all right? I need to know kung meron kayong problema. So yeah. Okay. So just some quick things here. I hope you find the codes I uploaded easy to read. The green ones here, or the green text here, are just comments. You can put a %sign at the start of the line or anywhere, and MATLAB will disregard anything that goes after the %. It will just be for the back-end user or the debugger or the programmer para basahin ano yung mga comments. So you can sprinkle comments in your codes just to let other people or even you what those lines do. Okay. So here, if you go to line 9, I hope kita pa rin siya sa screen. Let me enlarge it a little bit. There we go. So the matrix, I need a matrix A to play with this. So here I encode the matrix A. So the matrix A will have rows 1, 0, -2, 2. So by row yung pag-encode. And then if you want to go to the next row, lagyan nyo ng semicolon. Or by the way, matrices pala or vectors are enclosed in brackets in MATLAB. So dapat naka-bracket yan para alam ni MATLAB na ikaw ay nagme-matrix o nagme-vector. Okay? And then again by row. So this is the first row, -1, 0, -1, 2. You can separate row entries by a comma or simply by a space. So 2 space 0 space 2 space 0 will tell MATLAB, oh, the second row consists of 2, 0, 2, and 0. And then to get to the third row, semicolon, and then put that there. Oftentimes you want to suppress the output kasi ang gagawin ni MATLAB every line. Pag may pinagawa ka sa kanya sa isang line, i-output niya kagad yung result. If you're not interested with seeing the result for a particular calculation, medyo hahaba lang yung babasahin mong command line output, lagyan mo siya ng semicolon. Ipa-perform yung operation pero hindi niya i-display sa command window yung result. Pero what will happen is that if after some time you decided kailangan ko pala siyang makita, pwede niyo siyang i-display by using the command disp. Kung ano yung variable name that you assign to a certain quantity or a certain string of text, you can put it inside disp, parentheses, then gagawin niya yan. Usually pala parentheses yung mag-enclose sa arguments o yung inputs sa isang command. Brackets para sa vectors or matrices. Okay? Now, I mentioned this earlier. RREF is just RREF parenthesis A. Na-declare ko na si A sa taas. Pwede ko na siyang gamitin elsewhere sa baba ng code. Alam na ni MATLAB na si matrix A ay ito yung itsura. So B is equal to RREF of A. Kunin niya yung reduced row echelon form ni A. Dahil walang semicolon, kung ni-run nyo to, makikita nyo, pinakita niya kagad yung result. Okay? Though parang sa calculations niya, parang one time, big time niya ina-output yung result. Pero if you are doing a very long calculation, let's say this line takes a while before finishing, ipapakita na ni MATLAB yung result neto, or I mean, kung ito yung matagal i-run, i-output na ni MATLAB yung lahat ng nasa taas sa kanya na walang semicolon. So hindi tinatapos ni MATLAB yung buong code bago siya mag-display. So sabihin niya, pag walang colon, display ko kagad yung result. So kung ito ay matagal i-run, i-output ni MATLAB to habang nag-run to. So makita niyo na yung result kay B habang nag-run yung pagka-compute kay R, kung si R ay mahabang i-carry out. Pero mabilis lang naman to kasi 4 by what? It's just a 4 by 3 matrix. Sorry, a 3 by 4 matrix. So kaya mabilis lang yan lahat. And then I have rank and I have nullity. Now, MATLAB has this workspace. Depende sa configuration niya kung saan siya nakalagay. Pwedeng nasa gilid, pwedeng nasa baba. So you look at the workspace. This gives us all the variables that MATLAB already know at this particular session. So pwede niyong i-click ito or i-double click. Dadalhin niya kayo sa isang window na ipapakita niya ano yung laman ni variable A. Pero dito, alam mo na, may idea ka na, it's a 3 by 4 double precision matrix. Si B, na-compute niya na yan. So papasok na siya sometime into the workspace. You can click again on B to see how B looks like exactly. But here, you're given a brief description of what or how B looks like. It's a 3 by 4 matrix. Si R, yung rank, ipapakita niya na yung value. Si Z, ipapakita niya na mag-attempt siya na ipakita yung values. Pero kasi mahaba pa siya. So, hindi niya napakita lahat. And then this is also a nice check. Kasi pagka may laman yung workspace, and then you run another code, probably you run a different code other than example 55. And if unluckily, that code also uses the variable A, then there's a chance that MATLAB will use the variable A it already knows in its workspace in order to compute what is in the other command or in the other program. So yung workspace, ito yung magsasabi sa inyo, ano na yung nasa utak ni MATLAB. Ano yung nasa utak niya as matrix A, utak niya as matrix B, and so on. So ito lahat ng alam niya, nakastore sa memory niya. Pag nag-run ka ng program, kahit i-close mo to, mag-run ka ng isa pang program, sabihin mo A plus B, alam na ni MATLAB kung ano yun. Kahit huwag ka mag-declare ng A and B. Because in MATLAB's mind, it already knows the matrix A and the matrix B. Alright? Kaya kung plano nyo mag-run ng successive and very complicated programs, just to be safe, maglagay kayo ng clear command. If you write clear, it will remove all the variables from the workspace. So you can think of it as clearing MATLAB's memory, so you begin with scratch. Pero sometimes kung sequence ng programs yung iraran mo, sometimes kailangan mo yung value nito dun sa susunod mong iraran. Pero kaya minsan, ito yung usually pitfalls kung bakit mali yung output pero tama yung program. Kasi meron pa pala nakasave dun sa memory ng compiler for a variable that you used in the other program. So yeah, just be careful with those. Then here's how the output looks like. Line 9 was performed by MATLAB, but there was no output released because there was a semicolon at the end of line 9. Okay? But in line 11, I asked MATLAB to display the matrix A. And that's how this came about. So dun sa command window, makikita nyo, ito yung matrix na yon. So I displayed it para makita ko tama ba yung pagkaka-encode ko ng matrix A. Baka napagpalit ko yung column, napagpalit ko yung row, or may typo ako nagawa. Okay? So it's a good thing to check the outputs. Okay? And then line 15, find the RREF, walang semicolon. So right after MATLAB line 15, it will output B as this guy, which is exactly the B that we got, right? The RREF for A that we got in example 55. Okay, so hindi nyo kailangan manu-manuhin. And then, yung rank, alam natin, so kung, kunwari, ito lang yung alam natin. Oh, alam ko yung RREF, meron dalawang non-zero rows. So that means the rank is automatically 2. But again, thanks to MATLAB, in line 19, we asked it to compute the rank for us. And true enough, it gave us 2. Okay. And then last to find the null of A. But again, in MATLAB's parlance, yung null A ay dimension, ang null A ay isang basis para sa kernel ni A. Again, this is a basis for ker A. So the columns of the matrix Z will be the basis for kernel of A. And this is the basis that MATLAB gave us. Of course, these are not the exact values. They are just displayed up to 4 decimal digits. I think that's my setting for MATLAB. You can set to see how many decimal digits you want. If you want to get an exact or the machine precision for Z, kung ilang decimal places yung kayang ibigay ni MATLAB, what you can do is to click Z here. Tapos, i-open niya ano yung laman ng variable C, then you can copy-paste each of its entries. And I guess by default, MATLAB can output up to 16 decimal digits for real numbers. So, yeah. But since we are not interested with using the basis for the kernel for some of our calculations, then it suffices na ganito na lamang yung tingnan natin. Kasi anyway, ang habol ko lang naman ay ilan yung element ng basis ng kernel. Because the number of basis elements for the kernel is the nullity, right? So per column yung bilangan. So we have 2 columns here. So that means the nullity is equal to 2. Because we have 2 basis elements for the kernel of the matrix A. All right. By the way, MATLAB chooses to display an orthonormal basis for the null space. So what does orthonormal mean? We'll see it in module 5. But basically, pag kinuha niyo yung length nito, equals siya kay 1. So yeah, that's what the orthonormal basis means. But anyway, we'll talk about that later kung nag-wonder kayo bakit ito yung pinili ni MATLAB. Kasi sa napakaraming basis, pwede siyang pumili arbitrarily. Okay, but in any case, you're gonna get 2 columns, 1 for each basis element. And then you can do the same thing for example 56. You can play around with it. And then that's the end of module 4. Sorry, medyo humaba na naman. I always keep on trying to keep it 1.5 hours a meeting. But almost more than 2 hours na tayo. Any questions? None? Okay lang? Any concerns? Okay, gusto niyo na bang magdagdag tayo ng third problem for the homework? I promised kung magdadagdag ako ngayon, ang idadagdag ko ay problem 3, pagko-convert mula sa matrix papunta sa linear transformation. Or later na lang. Sama ko na lang siya sa module 5.
Yes, sir. Okay lang po bang masama siya sa susunod? Kasi meron pa po kaming isang requirement sa modern algebra. Medyo mahaba po.
Sige. Sure. No problem. So, yeah. So, I'll add that. And then probably 2 questions. Okay lang ba na 4 problems na lang for homework 5? Or you wanna keep it 5 problems? Time nyo na para maghaggle. So, 4 or 5 problems. Again, ang pro ng 4 problems only kakonte yung sasagutan. And most of you are halfway done kasi nasagutan nyo na yung dalawa. The con is that malaki yung weight ng bawat problem. Kasi magiging each problem will cost 25%. Or in fact, kung 5 sila, 20%. Pero, what do you think, guys?
Sir, magbibigay pa po ba kayo ng example for yung corollary?
Which corollary? Yung
reverse one.
Yung reverse? I'm not planning to.
Okay.
Yeah. Let's see. Yeah, kasi magiging basis. Ang tatanong ko lang ay magbibigay ako ng matrix. Hindi naman kalakihan. Tapos, nisip ko ay compute nyo lang yung linear transformation which exactly in the same light that I did here. May iba lang yung numbers. Just for you to experience how to convert from a matrix to a linear transformation. Let's see. Yeah, something like this. Example, you'll pattern your solutions with example 54. Probably siguro gawin ko naman 3x2 matrix. Tapos lagyan ko ng complex numbers na madadali lang naman. Tapos, anong vector space? Ako yung magbibigay ng vector space at saka ordered basis. So, magiging output nyo lang ay eto. ano yung L of V in terms of a vector. So siguro three-dimensional, siguro R3 to through M, siguro to polynomials na lang. Yeah. So ipapattern nyo lang talaga siya dun sa ginawa sa example 53 para magkaroon lang kayo ng experience how to do the other way around. Kasi ang dami nating examples pala na-realize ko lang. Ang dami nating examples, linear transformation to matrix. Pero isang example lang yung nilagay ko from matrix to linear transformation. So I guess it would be good if you will practice it firsthand with only one example para makita niyo yung dynamics ng gagawin doon. All right?
Okay, sir. Thank you.
All right. Okay lang ba yung 4 or you want 5? Di ba ako magpa-poll? Mabilis lang. Paano ako nagpo-poll dito? Oh, anyway, magpo-propose na lang. Hindi ko makita yung polling. Yeah. So let's make it 4 problems for homework 5. Any objections? Kindly raise your hand. Or send me a chat kung ayaw nyong bumoto ng hindi anonymous. Any objections? 5 seconds, 5.
Sir, pag 4, sorry, required po to answer all.
Yes.
Okay.
Pero ganun din kasi ang inisip ko for 5. For 5, required din to answer all. And then probably after that, we'll have homework 6. Tapos final homework thing 7. Okay lang ba yun? Para rin yung mga medyo, meron pa mga naiwan na backlog from homeworks 1 and 2 na medyo mabibigat, sorry about that, ay makahabol until the end of classes, which is, when is the end of classes? I think the last day is August 9. Tama ba? August 9, so that gives us first week of August and last week of July. So yeah, by tomorrow, you're gonna see the rest of homework 5, and then probably we'll have 2 weeks for homework 6. Ganito na rin, hatiin ko na rin yung pagbibigay para may nagagawa kayo in the meantime kasi medyo bumagal yung pagsusulat ko nung modules. So I was thinking, ano yung ilalagay ko dun sa... And then, sa last week, i-reveal ko na ba kung anong final homework? Wag na lang, surprise na lang yung final homework 7. Okay? Any other concerns or questions? Again, I would like to say this. I would like to appreciate all the efforts that you put into the class. Yeah. Tapusin ko lang. Baka malimutan ko kasi. Nakita ko yung gradual progression. Some of you really had a very hard time, almost at the point of giving up sa homework 1 and homework 2. But I see the progression even now yung mga dumarating na problem na solutions or answers to homeworks 1 and 2. They are really getting better and better, and that the development is there. So thank you for putting. I know you are putting a lot of effort into the class, so I really appreciate that. So that's why I will adjust the way I will give you your final grades. Of course, my basis will still be the percentage or the average of the percentages across all the homeworks, which, by the way, may problema yata si Moodle with homework 3. Hindi ko mabago yung denominator. Pero ang mangyayari lang ay dun sa final grade computation, kung pupunta kayo dun sa final grade page nyo, na-compute yung course grade as the average of homeworks 1, 2, 3, 4. Tapos, hinard code ko na over 30 nga ba? Over 30 yung homework 1, over 40 yung homework 2, over 20 yung homework 3, at over 17.5 yung homework 4. So don't worry, if you look at a particular homework, you see you get 71% even if you could have gotten, or you should have gotten 100% kasi mas maliit yung denominator. Hindi ko siya mabago sa settings ni Moodle, pero nabago ko siya sa computation ng final grade. You can also double check. Yeah, I think ito yung device for us para makuha yung percentage sa bawat homework. Homework 1, over 30, homework 2 over 40, homework 3 over 20, homework 4 over 7. And then if you average those 4 percentages, you should get the course grade that you have in Moodle right now. And there are probably 4 or 5 of you who got 100% right now. So yeah, that's great, guys. But we still have 2 homeworks left. Sorry, 3 homeworks left, 5, 6, and 7. Okay, so yeah. So I hope I get your consent to adjust what I said in the syllabus. Sabi ko, syllabus gagamitin ko yung standard UPOU conversion for the final grade. With your permission, just let me know until midnight today if you have any objections on that. But otherwise, I'm gonna come up with my own scale, but probably after you submitted homework 7 na lang para kita ko na yung distribution ng grades. Okay? So just let me know if you have any objections with that, but rest assured it would be for your benefit. I'll try to make it as fair and as beneficial to all, if not just most of you. All right? So I'll get your consent with that. So just let me know if you have any objections. And then, yes, Jeng, you have a question?
Sir, kung magdadagdag po kayo sa homework 5, ngayon po rin ba yung deadline?
Hindi. Of course, hindi. So yung problems 3 and 4 ng homework 5 probably will be due 3 days after I uploaded it. So i-upload ko siya bukas. By Wednesday siguro yung deadline. Tapos susunod na deadline natin ay Sunday, tapos susunod na deadline ay middle of the week for homework 6. And then ang deadline ng homework 7 would be on the finals week. Pero I hope to get your results before the final week for your final homework para ma-compute ko na yung grades nyo, ma-upload ko siya sa Moodle, makita nyo, makapag-comment kayo, and if you have some complaints, if you have some questions, kung meron kayong mga apila, you can tell me, right? Feel free to ask me about it, all right? Okay, any other concerns? If none, then thank you for coming, everyone. I hope you stay safe and warm this very rainy day. I hope you'll also you'll have the privilege to spend tomorrow with your family and to rest. Especially napaka bad weather ngayon in most parts of Luzon. So thank you all for coming, guys, and let's see each other again on Monday, same time. All right, bye, guys.
Yeah, bye, sir. Thank you.
Thank you.